Hi, and welcome to our 5th lesson in Chapter 1. Today we're going to look a little bit more closely at slope and some slope-related concepts. So we're going to just begin today by talking about the slopes of parallel and perpendicular lines, which I know you've heard before in geometry. If you recall, the slopes of two parallel lines, well, here's a set of parallel lines. In order for them to be parallel, they have to run exactly the same direction. So their slopes have to be exactly the same. If we apply that, we're asked to write the equation of a line that's parallel to this one, y equals 5x minus 9, but goes through this point, 5, 9. And I'm going to put an x1, y1 there. And say if we're going to write the equation of a line, we need to have a slope and a point on the line. So we need to be parallel to this one. That means we have to grab its slope. So the slope in this line is 5. We want to use that same slope with this point. And then we're to put our answer, it says, in slope-intercept form. The hint says that you should use the point-slope form, which I'm going to write right here for the last time. Y minus y1 equals m times x minus x1. And let's pause that video and let's write that equation in slope-intercept form. Here's my work. I used the coordinates of the point given, 5 and 9, along with the slope that we found, 5. In the point-slope format, I did the arithmetic to turn it into slope-intercept. So here's my final answer. The slopes of two perpendicular lines are definitely not the same. Instead, you may recall, so here are two perpendicular lines. The slopes of two perpendicular lines are negative reciprocals of each other. Negative reciprocal. And if you recall, a reciprocal is the upside down of a fraction. And so if we have a line whose slope, say, is negative 3/4, then a line perpendicular to that would have to have slope, opposite sign, and upside down, 4/3. That's the deal with slopes of perpendicular lines. Now this activity asks us to write the equation of a line perpendicular to this one, which passes through this point. And we're to put our equation in standard form. Let me just remind you, that's ax plus by plus c equals 0 according to our book. Some places say ax plus by equals c. It doesn't matter to me which of these two that we end up in. But we do have to know the slope of the given line, because perpendicular line is going to have the negative reciprocal slope. So there are my hints to you. I want you to pause the video. We're going to find the slope of this line. We're going to use the point slope form with this point, and we're going to write our final answer in standard form. Again, here's my answer. I took the given line, solved it for y so that I could find its slope, and that slope is 2. If we want to be perpendicular, we have to take the negative reciprocal of that. So the negative reciprocal of 2 is negative 1/2. I used the negative 1/2 along with the x and y coordinates of the given point, worked out my answer. This time, however, I didn't get to slope-intercept. I need to get to standard. So when I got to this point, I added the 1/2 x so that x and y are on the same side. I subtracted 5 from both sides to get the numbers on the other side. Then standard form, the requirement is the coefficients have to all be whole numbers. So in order to accomplish this, I had to multiply everything by 2. Okay, that gets rid of the fraction 1/2, if you will. So my final answer, x plus 2y equals negative 20. Very good. The next topic in our lesson is really about average rate of change. All of the examples that follow are related to slope, because really slope is the rate of change of 2 points, or the rate of change between 2 points. So the slopes of these two lines, since they're talking about the growth of number of people who live alone over a time span, the slopes of those lines will give us the average change in the number of people who live alone per year, or the average rate of change. It asks us to find the average rate of change, or the slope, for the men line here, and then interpret the result. I'm going to ask you to pause the video. You're using the ending point and the initial point, and we're going to do a slope calculation to find that average rate of change. Okay, will you pause, please? Here's my slope calculation. Boiling it down, the slope is about 0.25 to the nearest hundredth. As far as what that means in words, you know, folks, that this is not, if you're looking at the actual number of people living alone over a time span of 15 years, it isn't always constant. Instead, it will be up and it will be down, up, down, perhaps, and up, and down, down. But the average rate of change from start to finish is the slope of that line. What that means is, over that 15 years shown, the average change in the number of men who live alone is about 0.25 million per year. It's an increase of about 0.25 million per year. In a related topic, and again, all of these things are related to slope, if the graph of a function isn't a straight line, see, it might seem odd to talk about the slope of a curve. However, you can find the average rate of change between any 2 points. That would be the slope of a line between them. Okay, the slope of a line between those 2 points. And while we can't until we get to calculus, we cannot figure the exact slope of a curve, but we can look at slopes of lines that limit the curve. You may remember when we discussed slope in the previous lesson that we talked about the change in y over the change in x. That's what that little triangle, the delta symbol, stands for, change in. And so if we want the average rate of change between, say, this point and this point on that curve, what we do is find the slope. That is, we take the difference in their y's divided by the difference in their x's. Now we're going to apply that in several different ways. The first of our applications concerns a medicine that's been injected into a patient's muscle. The initial concentration was 100 milliliters, but we're interested in the amount of change in concentration between the 3rd and the 7th hour after the dose. So I'd like to have you just think about this for just a moment. If we wanted to put ordered pairs for this situation, time is the x, so ordered pairs would be in this format: time and y's are concentrations. Now if we're going to talk about an average rate of change, then we need to have the change in concentration divided by the change in time. Okay, that follows that same slope pattern. So let's look at what happens here. After 3 hours, the concentration was 0.05 milligrams. That's the point, 3, 0.05. After 7 hours, the concentration was 0.02 milligrams. And as we do this slope calculation, difference in the two y values, 0.05 minus 0.02, divided by the difference in time, 3 minus 7. On top, that's 0.03 change over a 4-hour period. And that is equal to 0.0075. So the average rate of change, oh, and it's negative because that was -4. Yeah, that makes sense. That means that in terms of words, between the 3rd and 7th hour, the concentration decreases by 0.0075 milliliters per hour. average rate of change. Very good. One more application, and this one concerns average velocity. The average velocity of an object is its change in position, or you might think placement or distance, divided by the change in time between the starting and ending position. So we're talking about some particle in space that at one point is here, but at the next time tick is up here, then that might be its trajectory, right? However, when we find its average rate of change, what we're going to do is look at its placement on some numbering system divided by the amount of time that's gone by. If you follow that through, that means that we'll want to take the ending placement minus the initial placement over the ending time minus the beginning time. With that knowledge, I'm going to ask you to think about this question. The distance in feet traveled by a ball rolling down a ramp is given by this function, 5 times t squared, where t is the time in seconds after the ball has been released. We are to find the ball's average velocity from the first time at 2 seconds till the second time 3 seconds. In order to do that, we got to know about the distance traveled. Okay, if we want to find the first placement of that ball, according to this function, it's 5 times the square of the time that's gone by and 2 seconds. So 5 times 2 times 2 is 20. Its position at the second time, well, you're following the same rule, but this time the time we're interested in has changed to 3 seconds. So 5 times 9, 45 feet is, these are feet from the initial position. Now finding the average velocity becomes an easy thing because we take the second distance minus the first over the second time minus the first. And we're talking 25 over 1, or 25 feet per second is the average velocity between the second and third seconds of this ball's travel. I'm going to ask you to pause the video and do the same thing for this interval between 2 seconds to 2.5 seconds. Here's my word for that problem. Again, the initial time, 2 seconds, was the same, so that first placement, 20 feet from the start, is the same. At 2.5 seconds, when 2.5 seconds have gone by, following the rule up here, then the placement, the distance traveled, would put it at 31.25 feet. We want to know the average velocity, or again, the average rate of change, if you will. We take the difference of the two distances divided by the difference of the two times. 22.5 feet per second is the speed here, or velocity, as you go from 2 to 2.5 seconds. Folks, if you think about that, it makes perfect sense. The way that gravity works, the longer something is in motion falling, the faster it will fall. So in a shorter time period, that average velocity is less than in the longer time period. All right, I'm sure we're going to have plenty of things to talk about in school tomorrow. Please don't forget to do that. You try, and we'll see you.